I'd now like to welcome our next speaker, Marvin Worthmann from Fraunhofer IAIS, who will talk about design of experiments. Yes. Marvin holds a master's degree in mechanical engineering, and as the title of the presentation tells, he works in design of experiments, informed machine learning, and Bayesian machine learning methods. The floor is yours.
Yes, I hope you can hear me. Thank you, Lukas. So hello everybody. My name is Marvin Worthmann from the Fraunhofer IAIS. And before I start with my presentation, I have a short question. Which one of you drank the coffee here at the summit? You liked it? Or you think maybe it's not that good? Because I love coffee, and for me it was quite nice, or quite well, I would say. But I thought about what are maybe possible solutions to make it even better. Can I change maybe some settings on the coffee machine? Or maybe it depends on the coffee beans itself. So to answer these questions, I will give you an introduction to our AI-based DOE solution that optimize experimental designs by increasing the data-driven processes. But before I start with that, I want to talk about the challenges companies and also we have right now to explain then what design of experiments is. And then I will show you how our solution goes even a step further. And if I'm good in time, I will tell you something about the Fraunhofer and the Fraunhofer IAIS at the end. So let's start with the challenges. The first challenge, or one of the biggest challenges, is increasing prices for energy and raw materials that leads to rising production costs right now. Research and development projects are getting more and more complex, and therefore they're also getting more cost intensity. But companies want to stay competitive, so they have to make investments in digitalization, decarbonization, and innovation, and still have the main focus on the sustainability. So all in all, we have this price increase, the research and investment pressure, and the sustainability aspect. And many of these challenges can only be addressed experimentally. So a lot of questions in the research and development can only be solved by virtual or physical experiments. And often only a limited number of trials can be conducted due to the high costs I mentioned before. And with the more and more complex problems and projects, you gain also a lot of changeable variables. And this is extremely difficult and time-consuming to get an optimal solution out of it. So improving the quality or the efficiency of products or processes is time-consuming and expensive. And to fit this problem, design of experiments is a really good solution. And now I will show you what design of experiments is all about. To get better insight of it, I will give a really raw overview about the developing process of a new product. So you have your planning phase, your experiment phase, and your evaluation phase. And this can take days to weeks to months or even to years, depending on your project, your problem. And in the most developing projects, the planning phase is an important one where all the important decisions were made. And this leads to the experimental phase, and at the end, your evaluation where you get your results. But when you have a lot of different variables, it's often really difficult to know how you can make the settings. How do you change or how do you make all the configurations to get the best solution out of it? Most people do it with this trial and error approach, or maybe do it like they read it in a paper or stuff like that. So in the best case, you have an expert who says we can mainly focus on this configuration or this configuration. But at the end, you hope to get the best solution, or maybe a good solution, or at least one solution. But is it really the best one? You don't know exactly. But with the design of experiments, you can get an even distribution about your working space. And let's explain this maybe into in an example I mentioned at the beginning, our coffee machine. So at first, I have to make clear which variables I want to use for the settings of my coffee machine. This is the first step in DOE. So that could be the temperature, the form grade, the grinding degree, the coffee amount, milk amount, or even some more variables. I don't know right now. Could be also the pressure. And you have to make clear which of these influences you need for your target, for your goal. And this leads also to the next question. What is your goal? This is really a challenging question you have to answer. And it's really a big problem because you have to make it clear in one or maybe two or three variables, but you have to make it really clear. And for our coffee machine, it could be maybe the taste or the caffeine amount, perhaps both. So you have to answer these two questions. Once you answered it, you come to your design creation, which is one of the biggest part of design of experiments. With this design creation, you create this so-called experimental design where you systematically cover your working space in even distribution. So when you imagine this room here is now my space, my experimental space. So all of you are maybe a possible solution for finding my best coffee settings. So if I change the temperature, maybe I come to you. You're my solution right now. Then I change maybe the pressure and I come to you. So in the worst case, I just observe this front area here. I don't know what is happening in the back. And I don't know if maybe in the back is a better solution than I just observe here. And with the design of experiments, I am able to observe my whole working experimental space and make some sampling points to get all the informations I need. And the big advantage of all experimental plans or experimental designs is that you need less experimental points for your experimental ones at the end. So when you do it with a trial and error approach, you maybe have 100 experimental points. With the design of experiments, you can maybe cover 50 or 20 or even less, and you get the same informations out of it. So with the creation of your design, you then go into your experiments and get your solution out of it. With your design and your solution, you train a model, and this model is able to reflect the reality as precisely as possible. So this model, with this model, you can change one, two, or even all variables, and you still get realistic information, a realistic prediction out of it, because you have this even distribution about your whole experimental space. And our solution goes even a step further. With our solution, we are able to use expert knowledge and historical data in this planning phase and experimental phase directly. We can implement them and use, instead of one big experimental phase based on one designing phase, we have a loop where we do our experimental phase several times. And let's get a closer look to it. So at first, we need some initial measurements. That is the base of all. But these initial measurements are much less than this traditional DOE plans should use. So with a few points, we can fit a curve with an uncertainty, with introducing an uncertainty, which you can see in this blue area. And in addition to that, we have also an acquisition function. And this acquisition function gives us a suggestion at which configuration, which point we have to measure again, which configuration of our settings we have to make a new experimental one and gain a new solution out of it. And with this new one, I hope you can see it with the red dotted point, with this new with this new data we gain from our suggestion, we can perform now new measurements. So we run new experiments and get new data. And this data we use to retrain our model. And with this retraining, we can reduce this uncertainty and get a better fit to the real world problem, to our real function. After that, we update our acquisition function again. And then we get also a new measurement point. This point leads us again to a new experiment where we get new data. So we use this data to update our function again. And then we update our acquisition function again. And again, and again, as long as our model fits our real function in the best way it's possible. And what are the big advantage of this solution? Well, first of all, we can reduce the number of trials by up to 50% with using this several experimental ones, because we need at first much less points, and all these points our AI suggests us are much better than all these traditional DOE plans would give us at the beginning. In addition to that, we are also able to detect systematic errors in the planning phase and in the experimental phase. So the problem is when you make just at the start in your planning phase a big mistake, and you mention it just at the end, you have to start again. And with our solution, we are also able to detect these errors just at the beginning. The problems are getting more and more complex, but with integrating knowledge from expert and historical data in this designing phase and in our experimental phase, we can also solve much complex problems with that, instead of using this normal developing phase or even traditional DOE plans. Because of this reducing of experimental points by up to 50%, we can also shorten our developing time for new products, for optimization processes, or stuff like that. And we got still a better modeling of our real-world function. We have less points, have a shorter developing time, but still got a better solution out of it. So we got a much better prediction model, which we can use to optimize our problem or optimize our configuration to get the best possible solution. And the last advantage is this higher utilization, because test stand and product lines can use in a very efficient way, because we can reduce all these experimental phases, experimental ones, by up to 50%. So the advantage our AI-based module has is this cost saving, the shortened developing time, and higher utilization by an early fault detection, a better modeling, and an efficient problem solving. But this is just right now theory, and I can talk this maybe the whole day. But and now I want to show you a project where we used our model, and this was done with Scheffler together. They had the problem that they want to determine the material properties of several steels, in detail the static strength. And normally they have to check them. And this test takes to 60 days and costs 12,000 euros to generate one data point. And they wanted a prediction model which predicts the material properties based on the chemical properties to reduce this runs of experiments. And our solution was a perfect fit for that. So as you can see on the top left plot, this is our modeling with this uncertainty area. And all the blue bullet point or the blue points are the suggestions from our acquisition function, where we have to measure again and make new experimental ones. But the most important plot is the last one. the third one, where you can see with the cross points all the real measurement points Schaeffler was doing in their test phase. So every time they have a new steel, they have to test it and make it in a kind of way. I will not go into detail because this would be too much. But with those cross points, you see how they have to, or how they checked their steel to get the optimal solution. And the optimal solution is here, this blue line. So you see that a lot of their measurement points are far away from it. So they're not necessary to check it in this configuration. And our solution shows in this, for you it's a little bit, it's not orange, for me it's orange. You can see in this colored area what our model suggested. So what we want to provide, which configuration Schaeffler has to do to get the optimal solution. And as you can see that this area gets smaller and smaller when you get more data points out of it. And at the end, we was able to save 50% of the data, experimental ones, Schaeffler normally has to do. So they have to make 8 ones with our modeling instead of 17 with their normal way. And they can save 100,000 euro for each test they have to make with your steel. And they make several tests all and all again. Yes. So I see there's a little bit time left, so I can tell you a bit about Fraunhofer and the Fraunhofer IAIS. So Fraunhofer, the Fraunhofer Society is an application-orientated research institute in Germany, I think also in Switzerland and Austria, if I'm right. Yes, I'm right. But here on the map, you can see just all the institutes here in Germany with 30,000 employees and 76 institutes, which all have a different main focus. The IAIS is based in artificial intelligence, machine learning, and big data in Bonn and Dresden. And we have 350 employees with 180 research and industry projects per year, also in different kinds of areas. So in my team, we are really depending on this DOE project, but we have also a lot of different projects we are working on. And normally our clients from all industries come from the DAX 40 to also medium-sized companies. So we are always open to gathering industry projects which fits perfectly in our area. And that was everything from my side. Thank you for your attention. And if you have any questions, maybe we can make a Q&A now. Otherwise, you can come to our stand at the Fraunhofer. Let's get in touch, and I'm happy if I can see some of you there to talk about my topic, or maybe over Fraunhofer in general. Thank you very much.
Thank you very much, Marvin. Somehow it got me intrigued into getting another coffee, so that was great. Thank you very much.